I am Máté Thurzó. I work in the Budapest office of the Liferay Budapest office. I'm the lead of the staging team. But this presentation is not about. It's not going to about staging. It's going to about using a graph database for analyzing your Liferay data. As I mentioned previously, I live and work in the beautiful city of Budapest. If you had ever the chance to go to Budapest, then you are lucky. If you have never had the chance, then go. During the summer, there are lots of festivals. It's a pretty fun city. What are you going to learn, or what are we going to see today? So basically, it's a long story, but how we started off working on the graph databases is that, as I mentioned, I'm the leader of the staging team, and we have been investigating staging for performance, to improve performance in staging. We realized, I will talk about it later, but we realized essentially staging is working with graphs, and then we ended up diving into graph theory. And then I was thinking that this can be used not just for staging, this can be used for lots of stuff, analyzing your Liferay data. So the idea for the presentation is, how can you have a database already filled with data because you have customers, you have information stored in there, you have your own workflows, you have your own content. Then how can you discover hidden or not so hidden relationships? How can you recommend? How can you do recommendation based on the content you have in there? And we are going to, in the first part, I'm going to give you a few examples of these graph analytics, very basic examples, and then we hopefully move gradually toward the more scientific part as the time allows us. So what is a graph? It's not the word graphs, not what you put it together in Excel. The mathematical formula for a graph looks like this. It's very descriptive. It's called an ordered pair. A graph is an ordered pair, meaning it has edges and vertices, nodes, vertices. It's basically the same concept, but this is a mathematical formula of a graph. We have been talking about science. The keynote had scientific aspects as well. And Jorge, yesterday, he had some science, machine learning involved and mathematics involved in there. So I thought I would kick off with this mathematical approach of graphs. So everyone knows what's a graph. I think it's a very simple concept. So this is from Wikipedia. This is a graph. The numbers with the circles are nodes, and between them the edges are the edges. So that's how you recognize a graph. Graphs comes in several flavors. We have lots of kind of graphs. We have graphs with cycles in it. We have graphs with acyclical graphs. We have directed, bidirected, undirected. Every kind of graph you can imagine, it's possible. So why we started working with graphs and what is this buzz about graphs? Basically, I think what Jorge showed us yesterday regarding machine learning is the top of the hype cycle, where graphs are not on the hype cycle at all. But graphs are interesting. Why graphs? I already told you that we've started off working with graphs because of staging, and then we moved from there. But basically, graphs are everywhere. If you think about your life, if you think about possible application of graphs, you realize that everything is connected. Human relationships, Facebook, if you go to Facebook, that's a sheer amount of nodes and edges and how they are interconnected. I mean, real life human relationships as well, at the workplace, in the family, and so on and so on. That's a big graph. Internet itself is a graph. It started as a graph with independent nodes, with hyperlinks linking them together, and other connections linking them together. Staging, as I already mentioned, it's a graph as well. And the human body itself can be a graph. Our brain is a huge graph. It's a huge graph of neurons. So that's an interesting topic. We'll talk about that later. So probably, if you think about your life, everything, everywhere, it's a graph. I actually stole this joke, so it's not mine, but I liked it very much, so I put it in here. So probably, if you think about a problem, it has a graph representation, or it can be interpreted as a graph. And if it's a graph, then you can use graph theory and graph algorithms on it. So graphs are fun. I know this is sort of a geeky statement to make, but I like graphs. I don't know why. Hungarians have a tendency to like graphs. Hungarians were big in graph theory, also later on that. But graphs are easy to work with. So if I show a graph to my father who has no IT knowledge whatsoever, even though he can share the Wi-Fi from his mobile phone to his tablet now, but basically, he has no IT knowledge, so graphs are easy to work with. So if I show this graph to him, for example, and this is the Neo4j console, we'll talk about it. So this is an org chart within the engineering team. It's not complete, but if you take a look at it, we have these nodes. I have myself here. So there are these edges. The edges say that Maya reports to me, and Ákos reports to me, and Daniel reports to me. But I reports to Julio, and Julio reports to Jorge, and so on and so on. So it's simple. It's a very simple concept. If I show this to my father or my mother, I can tell her that, see, mother, I need to move up the graph to be more of a boss than I am now. So with the year-end reviews coming up, I can show this to my bosses as well, that, see, this is the path I need to go up to. Just kidding. I'm happy where I am now. But the point is that it's very easy to use, it's very simple to use, and it's an easy concept. So graphs are easy to work with. Graphs are whiteboard friendly. If I go ahead and we don't have a whiteboard here, but if I draw, like quickly sketch up a graph, it's easy to understand as well. It's very easy to model a graph data structure if you have the clear vision before your eyes what you need to do. And graphs are cool because you can use graph theory, because you can have graph algorithms, and probably if you have a graph kind of data structure, applying the graph theory algorithms on that, it will be more performant. It will be more performant on a graph database than, for example, a traditional relational database. So that's a huge advantage for graphs. What kind of graph database is out there? So basically, the market leader is the Neo4j, but the close second is the OrientDB, and I would say the close third is OrangoDB. But MongoDB has recently released a new version of its database, of its product, and they are including some graph database capabilities in MongoDB as well. Well, we started off with Neo4j, so there is not really, so I'm not marketing for Neo4j. I have no affiliation with Neo4j. Simply, we started off playing around with Neo4j, so that's the reason I'm using Neo4j. They seem to be the most mature product, though, for me, but that's absolutely a personal perspective. They have stored procedures, they have a native graph storage engine, and so on and so on. There's a lot of things I like about Neo4j. They have this cool query language, Cypher, which is also very nice. I'm going to use Cypher, the Neo4j query language, and what you see previously, that's the Neo4j console, which is very easy to use as well. So first, we need to somehow get the data from Liferay and put it in the Neo4j in order to do this fancy stuff I'm promising you will see. So first, we have the Neo4j stored procedure approach. Neo4j released, Neo4j stored procedure is essentially a Java library. So it's a jar file, you put it in the Neo4j database as a Neo4j plugin, and you can call as a procedure. So they have this epoch library. It's a set of useful utilities written in Java for Neo4j. They have this especially very useful stuff we've been using is basically a JDBC driver that you can connect to your Liferay installation and then pull data from the MySQL, in this example, to Neo4j. So first you need to load the driver, and second you need to parse the data. Here I've used as an example. Don't look at the password because it's very complicated. But basically this is a Liferay database pulling up the bookmarks entry table and then creating nodes based on the bookmarks entries. And then I'm doing the same with users. And then as a last step, I'm connecting between them. So we can have the graph structure and graph data I was telling you about. There's another option which there's more Liferay to it. So basically, that's the background task executor approach. Neo4j issued an official Java language driver, but that's not OSGI compliant. So we took the language driver and then we made it now OSGI compliant. It's accessible on GitHub. It's under my name. So if you go at the @ Máté Thurzó, then you can find the Liferay Neo4j driver. You can just drop it into your OSGI container, and we are exposing the necessary packages you need to access from your OSGI bundles. So we are going to improve that hopefully later on. So basically, this is a background task executor class. How many of you heard about the background task executors in Liferay? Pretty much of you. So this is basically developed for staging, but people started using it as totally different purposes than staging. And this is basically this can run a background process on a separate thread from the Liferay installation. And then this is another approach. How can you load Liferay data into your Neo4j instance? It's not difficult. If you know Java, then you don't have any surprises here. So that's pretty simple. Now, we have our data now. So let me show you the example data set I created for this presentation. And this is in the top. So sort of I started off working with the org chart approach here. So we have the yellow nodes are persons, the green nodes are content they have created. The green nodes have categories. The blue nodes are the categories. So we've categorized our content. And then the red nodes are tasks. I'm going to use them for later. So you can see here that Julio, for example, is interested in music. Julio is my boss, and he has a band called Cabina 14. They are very good. Bilus is not his band. And they have both the same category, which is music. Maria was created a content music history, which also has the same category as music. And I am sort of a motorcycle enthusiast. I have created Ducati and Kawasaki content, and then it has the category bikes and cars. So simple. So that's one of the power of graphs. Okay, let's move back to the presentation. So this is the data set we are working with. The first question we might want to ask is, who does Jorge manage? So that's easy to ask from a graph database. Who does Jorge manage? And I already have the result of that somewhere. This is it. So who does Jorge manage? Julio, Chema, Sergio, that's 3 persons. So if we go back to the org chart, then we can see that here's Jorge. Jorge manages Sergio and Chema and Julio. That's okay, but Jorge is the vice president of engineering. So who does Jorge manage in total? I mean, not just the direct employees, but we are interested in everyone that Jorge manages. I'm not going to jump back and forth between the presentation mode because it's very slow. So basically, that's the query for who does more Jorge manage. And then adding a little star, you can see here that there is this little star that's different. So basically, that little star tells Neo4j to traverse all the paths for the given pattern, and then that's how you got all the persons, all the employees Jorge manages. So essentially, you will see all of the persons within the engineering. So just a few words about the Cypher language. So Cypher is especially created for graph database operations. So it's nothing like SQL languages, although it has some similar approaches. So with Cypher, you have, instead of select, you have this match keyword, and then this match keyword usually tells the graph database that you are looking for a pattern. This is a pattern that we say that we have this J node, which is a person, and then we have the direction defined here, and we have the label of the relationship, which is reports to. So what this query tells me that essentially I'm looking for persons, nodes that are connected with Jorge, with the edge, reports to. And I'm not just interested in the first iteration, not just interested in the first neighbors, but I'm interested in all the neighbors. So let's move forward and add more content to our database. I showed you what kind of content do we have. So we can ask more detailed questions like who are the content creators? So if you are running a news site, or if you are running, for example, Twitter or Tumblr, and you have an extreme amount of data in your database, in your graph database, who are the content creators is a valid question, because you want to know who are the most content creators or who hasn't created any content, right? So with this simple query, I'm showing you here. This is very simple query. So this is telling me who are the content creators, who can create content. Maybe in case of Twitter or Facebook or Tumblr, the more valid question is who hasn't created any content, because maybe that account is dead, so we might end up deleting it, or we want to know that why they are not creating any content. So this is a more complex query, but still it's not very difficult. So I basically wrote these Cypher queries without very deep knowledge of Neo4j. So this is, I think, very powerful that you can simply asking questions and writing the answers for that in a very timely manner. Okay, so this is the result of who are the content creators, and this is the result of who are not the content creators. So it's all working. Believe me, even though I'm not running the queries, it's working. So the next interesting part is recommendation. So not just because basically with Neo4j, the purpose, and with graph database, the purpose is that you can build a recommendation, a real-time recommendation system. And obviously you can talk about that for hours, but we don't have much time, so I'm giving you a few examples. So typical in the social media, who to follow. I'm logging into Facebook or Twitter, who to follow. I have interests, I have created content based on different categories. So what does the system suggest me that I should follow, because probably we have the same interest. So in this case, I picked myself. I'm interested in bikes and cars, so I'm looking for people who have created content that has the category bikes and cars, and they are not me, because I know me, and we share the same interest. So basically, with Neo4j, it's easy to say that, because it says that Donny, my colleague, he also has a motorcycle, he also has a Kawasaki. He's sharing the same interest. And surprisingly, I didn't know, but the vice president of engineering created an article regarding motorsports, so he has the same interest. Cool, that's something new I didn't know. So maybe the system, when I log into Liferay, it can suggest me that I should follow Jorge, or I should write to Jorge because he has the same interest. Now, the next question is that because Donny is one hop from me, because he's my direct employee, so the chances are that we already talked about bikes and cars and motorcycles, because we meet every day. So the next question is that, okay, how far they are from me? This far can be, in this example, the distance function, I defined how far is meaning that how far is he from on the org chart, because Donny is one hop from me, so we probably talked about this, but Jorge is 2 hops from me, so we might not have talked about this before. So it's a little bit more complicated. So basically, I'm measuring the distance. This is the query for it. I'm measuring the distance of how far Jorge is from me. And if you look at the results, so this is the result of who sharing the same interest, and this is the result of how far they are from me. So this is tricky in Neo4j, because in the graph view mode, they are returning only the nodes. But if I click here, you can see here that Daniel is one hop away from me, and Jorge is 2 hops away from me. So maybe the who to follow portlet or who to follow application can say, okay, we should put Jorge first, because chances are you've never talked about bikes and cars before. Okay? So these are very basic examples. Obviously, a social media or an e-commerce application can pose more complex questions. But you saw that with typical who to follow kind of questions, what kind of interest, it's very easy and very simple to write queries to understand your customers or your users' interests or behavior or this kind of stuff. So e-commerce and social media works this way on a more bigger scale. So I want to stop here for 1 minute though. Typically, these problems can be solved in MySQL as well, or in relational databases as well. We have tons of technologies, tons of ways to do this stuff. And graph databases are not the silver bullet. They can help, and they can be used to write quick queries for them. So you might end up using another technology. So very quickly about staging. I'm the staging lead, and I already told you that we have started off with staging. Staging, how many of you know what staging is? Most of the people. Good. So it's an advanced publication tool. It's used for replicating sites between instances or content between instances. So basically, staging is operating on an entity graph, and this is no. We are going to skip that because I'm running out of time. So staging is operate on an entity graph. You can imagine that this is a very simple scenario. We have the yellow is web content, the green is images. We have a blog and a web content folder. So these entities are connected. This is an entity graph. It's very simple. Once again, we spent sort of half a day to think about how can we speed up staging, and we realized that the answer to our questions is topological sorting and the Kaufman-Graham algorithm. So topological sorting is when you traverse a graph and you define a certain order of the nodes. And the trick about the Kaufman-Graham algorithm is that it's not just any order. So the Kaufman-Graham guarantees you so basically there will be a set of nodes and everything needs to be exported or processed first, will come first, and then every other nodes rely on the previous nodes will come after them. So it basically creates you a list of nodes that will be guaranteed to be processed, exported, and imported in the proper way. So this is it in theory. We can import the images first because the images doesn't depend on anyone, but content depend on the images. So that's topological sorting. Different topological sorts are available. And then basically, the most important part that for staging, it has to be a DAG, a directed acyclical graph, which it is, as a matter of fact, and it should work. I have 5 minutes left, so I'm going to speed up. This was the practical usage. The next one is the scientific usage I'm really fond of. So there is a thing called Hungarian algorithm. How many of you there is a Hungarian algorithm? I didn't know there is a Hungarian algorithm. I found it day before yesterday or something like that. Hungarian algorithm is a thing. I haven't invented it. Basically, Hungarian algorithm works on a bipartite graph. It's basically solving an assignment problem with the help of a cost function. So a bipartite graph is like this. We have two sets of nodes, and the bipartite graph will be is bipartite because every edge is starting from one set and has an end in the other set. So we can see here that every edge in this graph has a start in the U set and has an end in the V set. So that's the typical problem. I copied from Wikipedia that we have 3 workers and we have 3 tasks, and they have a cost, how much money they are doing the task for. So Armand is working, Armand is doing the cleaning bathroom for $2, but sweeping the floors for $3. So for me, what I need to know is that obviously I want to be cost effective. So I go ahead and pick Armand for the cleaning bathroom, Francine for the sweeping floors, and Herbert for washing the windows, because that's the less amount of money for me. So yeah, this is an assignment problem. Hungarian algorithm then give you this solution and give you this assignment in a scientific way. If we take one step further, though, the Hungarian algorithm can assign tasks with this cost function. The cost was a static value in the previous example. So, for example, I have 3 employees and I have 3 tasks. And the cost function in this case can be an advanced mathematical model based on my employees' experience, by years, how many years have been working with Liferay, and what field are they working on, and so on and so on. So, for example, Maria is a QA engineer, so writing a unit test she should be very comfortable with it. But maybe fix a bug in background task executors, it's not her cup of tea. But Daniel, for example, he's a senior engineer. He wrote most of the background task executor framework, and the system might know that, so he can end up doing that. The point is that based on this experience of the people, we can define a function that basically produces a number, and then we can assign the task in an automatic way. A system can assign the task to the employees. Okay, so this is, I'm going to skip most of them because I don't have any more time. This is something I wanted to mention. How many of you heard about the Panama Papers? So then you know that it was a huge scandal, and then basically the Panama Papers, it was originated from the Süddeutsche Zeitung. They had a data leak, 4 gigabytes of data. Journalists went ahead and they uploaded everything into a Neo4j database, and then they started to look into the database. What they did is actually they didn't really have any science to it. They just clicked around in the graph and see if there are politicians connected to fraudulent activity, like they are evading tax and so on and so on. So this is one power of the graph. You don't have to be an IT person to just discover the graph, because it's simple that this politician at some point is related to this politician's company, who has a company, and so on and so on. So this is good. The graphs have, so this is more advanced, and I've read some articles about that pharmaceutical companies starting to upload brain structure and cell structure into graph databases, and they are running machine learning algorithms combined with graph theory algorithms to find a cure for cancer, for example, because they try to pattern match the graph. So obviously, this 100 nodes of graph is not a real data. What they upload is that millions of cells and millions of examples into a graph database. And what they do is they try to find patterns, because the cancerous cells has a proper pattern, how they look like, and they want to find the same within a graph database. So it can help pharmaceutical companies. He's a Hungarian guy. I told you that Hungarians have sort of a thing for graph theory. He's teaching on the University of Chicago, and last year he issued a paper about graph isomorphism, which is basically pattern matching on graphs. And he claims that graph isomorphism can be solved in a quasi-polynomial time, which means faster than before. So, but this is sort of a theoretical progress and has no practical usage so far. The last section, in the 1 minute I have left, I want to talk about predicting the future and predicting things. So there is a thing called random graph. Random graph is basically a probability applied to graphs. So you can say that what is the probability that we will have an edge between 2 nodes, or what is the probability to have this amount of nodes, or how the graph will look like. And this is very useful in complex network modeling. Imagine the situation if Facebook has this knowledge and they can predict what kind of relationships are we going to have, how our friends will look like. Are they going to be foreigners or Hungarians, or what are their interests? So this is a huge thing for random graphs. Another Hungarian, he is Paul Erdős. He was sort of a rock star in mathematics and in graph theory, and he laid down the basics, the foundations of random graphs. And then there is another Hungarian who developed that idea, but he is not in the presentation for now. So the homework is, Jorge gave you homework, so I give you homework as well, because I really like the idea that look up these people and read about graphs. And remember, everything is a graph, and everything can be handled as a graph. We don't have time for questions. But there is a coffee break coming up, so you can find me if you have any questions. And I'm going to upload, I already did upload some of the gist, some of the code pieces to GitHub, so you can look it up and you can play around with it. Thank you very much.